Start.
Okay.
Yeah. Good evening and welcome to this evening's session of the satellite event of ICW IP 2023, workshop on teaching physics effectively online and women in STEM. As a part of this satellite workshop, we now have the public lecture by Professor Vandana Sharma from IIT Hyderabad. Dr. Vandana Sharma did her PhD from PRL in the year 2007 with Professor Bhas Bapat. She worked on momentum spectroscopic studies of atomic and molecular ionization during her PhD. She moved to JILA, University of Colorado at Boulder, followed by Max Planck Institute for Nuclear Physics, Germany, for her postdoctoral work. She returned to India and joined the Indian Institute of Technology, Hyderabad, as a faculty in the year 2012. She has worked on ultrafast dynamics of small molecules, along with developing different equipment, not only for fundamental studies, but also for imaging biological systems and samples. She is in the editorial board of Frontiers of Physics, Atomic and Molecular Physics Journal. She has won the Sheldon Young Scientist Award and recently awarded the Sri Ramakrishna Paramhamsa Research Grant Award. She loves trekking and sheds all her stresses in the mountains. We now invite Professor Vandana Sharma to deliver the public lecture.
Yeah, thank you. Thank you, Madhurima, and thanks the organizer, Sai Preeti, Vandana, and all everybody behind the curtain. And thanks for giving me the opportunity to present my work here in this forum. So the thing which I'll be talking about, just pardon me if it is below the level, but I have tried to, I thought that most of the students from the Deaton University will be here. So that was the reason for presenting my talk like this. So it is mainly based on the imaging technique which we have been using, or the equipment which I have built over the past 11 years, which I have spent in this beautiful institute. I can move. Okay, so maybe. Yeah, in this institute, which is almost 15 years old. So it was, I mean, when it started, there were only, in 2016, we moved this to permanent campus. There were only 3 buildings then, which you see here. These were the only 3 buildings which we had. Now, if you come to the campus, it is actually transformed into a really big campus now. So please come and visit IIT. It's a very beautiful campus. So in this campus, when I started, there was nothing. Even buildings were not there. So the things which we had, not even the funds. So the things which we had was N. Krishnamurti, who have. So he had donated few of the chambers, and with those chambers and the steel bars which were lying in the lab. So from there we started making some spectrometer, and this is what the output of the steel which was lying in the lab, and we have made really a beautiful spectrometer out of that, and that is what actually gave us really beautiful results, which you see in the slide. So these are just few glimpses of the part of work which we have done. And it is quite a lot. I mean, sorry, I don't want to advertise on this one, but yeah, basically we started from nothing, and yeah, it was really, I feel proud that with me, with the help of my team at IITH, we are able to do lot of science, and along with the application imaging as well, which you will see eventually. So these two, anyway, I will be presenting today. This one I will not be, but we have we study small molecules. I mean, from atom to the molecule, little bit complex, and we have actually moved towards imaging the tissues and all. So this is how we have evolved over last 11 years. So the whole talk I will be presenting from a diatomic molecule, where we will be trying to freeze a small molecule, small diatomic molecular ion, singly charged molecular ion in this space. This will be my first part of the talk. in the same scenario, if I make it can mimic the diatomic molecule. It is, you can see that this is a CS3I molecule. It is more like a diatomic molecule because there are two candidates, two big bulky atoms in there. So you can mimic that, and then if you little bit tweak the laser parameters, we can have highly charged ions as well. So this will be the second part of my talk. And in third part of my talk, I will take you to the application side, where we are trying to make one device where it will be an automated device, where the robot can actually do the IV. The intravenous therapy will be done by a robotic arm, and that we will move towards the end. So this three is overall, I have put in one umbrella of imaging. So how are we? So in the first part, so to do the ions, to see something which you cannot see. So that actually is basically we have made, that is called the Ion Spectrometer, where you ionize the system, you make the ions, and you push them by the electric field. The same 11th, 12th physics one has to apply. You push the ion towards the detector, and you push it in such a fashion that certain kinetic energy will be focused at one position or on one circle. So this is the idea is not very new. It was actually discovered by Epping and Parker, but we have actually provided a very good recipe to study the kinetic energy without actually using dependent on the photon sources, which we don't have in the lab right now. So this whole system is basically 3 electrode system. You have a pusher plate which pushes the ion, then there is a puller plate which attracts the ion, and then you just put it on the detector. So lower energy ions will be focused at the center, higher energy will be focused at the periphery. So they will make like the onion. So you peel out the onion. The outer one is basically having the more energy. You peel out the onion and coat deeper and deeper. The inner circle, when you reach, that is the lowest energy ion which you actually are detecting, and that gives you the history from where these ions have come from. And history means the energy levels they are born with. Okay, so every atom has, there are discrete energy levels. So is true for molecules as well. Okay, so that is what we try to study. So this instrument, so you have, how do you really probe it? So this is the imaging instrument. You probe it with the photon. You can use any source. Basically, if I have to see inside the atom, I have to inside. Let's say I have to see inside the apple whether the seed is small or big. I have to cut it, right? So likewise here, we have to cut the atom, cut the atom, and we can cut it by any source. So here what we are using is the ultrashort laser pulses. So here the parameters for these laser pulses are like, you have the energy is something about 30 microjoule. We have 25 femtosecond pulse duration. I mean, it survives for 25 femtosecond. The wavelength is somewhere around 800 nanometer. These are the peak intensities. And here we can actually change the intensity, and also we can change the wavelength by just doubling crystal. So when you combine this laser source and our spectrometer, this is the laser source and the spectrometer, it actually, what you get in your hand is basically, this is the laser pulse which comes in. Sorry, this is not visible here, but there are 3 electrode systems. So there is one electrode here, then there is another electrode here, then there is a laser focusing here, and then they are pushed on the detector. So the thing which we get is the time of flight and the position image. This is how it would look like, and this is what I was talking about, has the onion slices. So this is the oxygen molecule. So the kind of structure we see, if we just take a slice of this time of flight, the middle slice, the resolution in the position spectrum is even more better. What you see here is quite, so there are 4 loops here, and it's not very good resolution at the lower energy, so we are not looking into this one, but the ones which are having the higher energy, we can actually look into it. So we can so we need to know that what is the energy, and we can actually calibrate the energy. So this is as I told you, that lower energy will be hitting at the center, higher energy will be hitting at the periphery. So I can know the energy. So this is how I can generate the energy equation. This is the calibrated energy equation, and I can know the energy of the ion. So once I have the energy of the ion, I can start understanding the ion. So this is how the energy spectrum of the oxygen ion would look like. Okay, so now if you look at the molecule, so in a molecule, what is basically the orbitals have a different shape. So like in atom, you might have heard of s orbital, p orbital, d orbital, right? So s orbital have the spherical symmetry, then p orbital has a pi kind of a structure, then you come to the d orbital, it has 4 lobes like kind of structure. Like similarly in the molecule, this happens, right? So then the highest occupied molecular orbital will be having this kind of shape. This green, this blue which you see, and this red which you see is the electron cloud. Okay, and the solid ones which you see are basically the nuclei of the two atoms. This is oxygen. This is oxygen. Okay, so when no light, so this light is linearly polarized. Linearly polarized means there is an electric field which is oscillating only in one direction. Okay, and this electric field can only, so when this electric field has this is the nuclear axis, when the direction of this electric field is about 40 degrees, so electron has the probability of getting aligned in this one, and then that can actually escape out of the molecule. Right? So if the molecule is aligned in this way, so electron will go out, and then the ions which will be flowing apart will be detected as a 4-lobe here. So ions can come here, can come here, can come here, and can come here. So this is what we see here. So we can actually back calculate what are the energies actually they are coming from, and we can essentially so this is the highest occupied orbital of the molecular oxygen, which is pi symmetry. So this is not, this is actually quite intuitive that the ions will be flying at an angle of 40 degrees, right? So this was already predicted by ADK, which is these are the 3 scientists who had actually tried to calculate the tunneling ionization and calculated the symmetry of the ions, the way they will be coming out. So when we increase, so what is happening here, when we increase the intensity with 800 nanometer laser pulse, what we see that these lobes try to actually pull together. They try to they try to come together. This is the polarization direction. You see that as we are increasing the intensity, so the lobes are coming together and it becomes more of isotropic. In this direction. So more of, the ions are hitting at this point and this point, right? So they are not, you don't see any 4 lobes here. But so here we say that molecule is basically, you are applying the electric field, the ion is being pushed like that, right? But the moment you change the 800 nanometer, this is not happening. You are changing the electric field. This is not happening. Why molecule is not rotating? So what is happening at this point? So 800 is able to rotate and 400 is not able to rotate. So now you have to go deeper, little deeper, and track that where the molecular ion has come from. So now we need to really look into the thing what is happening here. So when we looked into, this is what we had, and this contains all the information. So the low energy ones, as I told, are not very well resolved. The one which is resolved was this high energy one. So when we looked into it, so what we saw that these are energetically allowed state is that the electron gets ionized, and the nuclear wave packet lie in this state, and eventually it evolves. They are actually going far away from each other. So it is getting into the dissociative state, and the way it evolves is going from quartet pi Ungerad state to singly dressed quartet sigma Gerard state to doubly dressed quartet sigma Ungerad state. So these are the three states which are actually being participated for this transition, for this particular case. So when we try to understand that why molecule has to rotate, so we need to bring into these states in the electric field, and we wrote the equation, Lagrange equation. So there is a polarizability of the states which are lying in here. So this is the electric field direction of the laser pulse, and this is how the molecular ion would has been oriented, and it can orient in any of the direction. Okay. The ones which are around 40 degrees will have a higher chances of getting ionized. So, so this is the electric field direction. So you see that there is a polarizability alpha parallel and alpha perpendicular. Alpha parallel is the polarizability along the electric field, and alpha perpendicular is perpendicular to this one. So this delta alpha here will decide whether this molecule will rotate or anti-rotate. Right? So now, when we looked into it for 800 case, what we saw that the whole pulse actually stays for 25 femtosecond. Within that 25 femtosecond, the molecule actually is basically still in quartet pi Ungerad state. Okay, so when we calculated the polarizability of it, it is basically delta alpha, which when we calculated, it is positive. So this means the molecule actually is rotating. But at 400, what we see that this is at this particular this is almost of a 35 femtosecond pulse. So molecule goes in this quartet pi Ungerad state, and there is substantial intensity over here as well of the light, which actually where this quartet sigma Ungerad state also is there. When we calculated the polarizability of it, this is basically the negative. So the electric field of the laser is trying to align, but the negative polarizability is trying to anti-align. It is like कि oxygen. So there is a dialogue in the movie, one of the movies, कि उसको liquid oxygen में डाल दो, liquid उससे जीने नहीं देगा, oxygen उससे मरने नहीं देगा. Same thing, ये electric field is trying to align it, but this delta alpha is not trying to. It is trying to anti-align it. So it appears frozen, and that is what is happening in our case.
I just want to clarify one thing.
Yeah.
You use the word Gerard state and Ungerad state. That's odd and even state.
Yeah, those are odd.
Oh, okay.
Yeah. Those are odd and even.
No, you use the term Gerade and Ungerade.
Because those are German scientists, so
German terms.
German terms.
That's what
I'm
confused about that. Yeah.
I think maybe we'll take questions at the end because it's a full public lecture.
Yeah.
Public lecture, so it may be easier if we take questions.
Yeah. So now, so this is so basically at 400, the molecular ion appears frozen, and we call this as the transient negative polarizability. Basically, it is frustrating the alignment, so it is not allowing it to align it. So the more details you will find in this paper, which was published in 2020, somewhere around that. Now, coming to the next experiment, where we are keeping almost same. It's just laser is same, so parameters will also be the same. The only thing is that whatever is in our hand, we can change. So there, what we try to change is the pulse duration, and the intensities were kept constant there, and the only thing which we changed there was the pulse duration. We tried to stretch the pulse as much as possible. So the range which we actually changed it to from 25 to 1500 femtosecond. Now, Same spectrometer, velocity mapping spectrometer was there, and we put the light there and then allowed the CS3 ion interact with the laser pulses. And what we saw at the two extremes, so we took many data in the element, but I just showed the extremes here. So at the 25 femtosecond, what you see is very few ions, and those are all of them are basically singly charged ions. But at 1500 femtosecond, we start to see multiple charged ions. You see that this is CS3 I plus ion, this is a parent ion. We have I plus ion, then we have a double plus ion, then we have CS3 segments. So it's basically CH plus, C plus, all segments are there. So there are lots of intensity is same. So what is happening there? So if we can crank up the intensity, it is quite understood that if you crank up the intensity, there are lots of photons available to ionize the system. But it is not but at lower intensity, what is actually happening? So we try to understand further. So this is just the zoomed in view. So you have this here at 1500 femtosecond, we have quite a lot of ions. Again, more fragments here at 25 femtosecond and 1500 femtosecond, we see that there is a I double plus ion formation as well. Okay, so and we start to see that what is it actually increasing? So we just took the counts, and basically it is continuously increasing, and then after maybe 600 femtoseconds tries to stabilize. So now we look into the energy levels, and that those energy levels actually come from velocity map imaging technique, and we did that. So we just took the two ions here. And these are basically the ones which are Coulomb exploding, and those ions are coming together. So like if CS3 I double plus, if there is you remove the two electrons, so that CS3 I double plus can break up into CS3 plus and I plus. It can also break up into CS3 neutral and I double plus. So what I am looking at is the one which is basically equally shared, and then maybe we can actually extrapolate the same thing for the highly charged ions and say that this is the reason why we see the multiply charged ions. There are highly charged states where we see that. So when we look into it, so this is how the electrons are arranged in CS3I molecule. And this is the X tilde state, where we have the highest occupied molecular orbital is basically E state, which looks like something like that. Okay, so this is the nuclear axis. You can say that this is the internuclear axis, and this is the 2e state, where this is how the electrons are arranged, and in the 3e state, the electrons are arranged something like that. And this is the direction of polarization. Okay, so this one, if the electrons are arranged, if somehow you see that electrons are aligned along the direction of polarization, we can actually kick out the more and more electrons. But this is deep seated inside, because this is the valence shell. This is, however, one shell below. This is HOMO -1, highest occupied molecular orbital -1. Okay, so this is the highest occupied orbital. So where you can actually kick out the electron. So both states are actually probable in this intensity which I am talking about, but we have that singly charged electron. So, but what is happening? What is actually leading to the multiply charged state? So basically, when we did the calculation and we took out we removed the first electron, and this whole CS3I plus ion, it tries to evolve over the time. So when it evolves, they are actually getting separated apart. So that this distance is increasing. Okay, so when distance increases, basically when the distance is increasing, so those two states which I was talking about in the previous slide here, these two states, they actually, as this R is increasing, these two states are coming closer. And you can couple it with one photon. When you are able to couple exactly with the one photon, we call it as the resonance process. Okay, so basically, for the longer duration, what is happening that for a shorter duration, we are not able to reach to this point. For the longer duration, we are able to reach to this point where we still have the photons to couple between these two states. And when the electron actually can couple from 3A to 2E or 2E to 3E, So which is aligned along the polarization direction, and we can eject the electron out. And that is that is the reason why we are able to see that the higher charge states for a bigger pulse duration. So as a summary for the whole fundamental science result is basically we did oxygen and the CH3I molecule. For oxygen molecule, we tried to we changed color from 800 to 400, and what we saw that because of the transient because of the transient polarizability, the molecular ion appears frozen. For CH3 ion, so when we increase the pulse duration, what we are able to see that we are actually able to populate highly charged states, and we are seeing highly charged states. So more details again can be found in these two papers for those. So now let me take you to the journey. So this was one of our, since my PhD days, I always wanted to make devices, and that is what I am trained also. When I joined Haas Bapet in during my PhD days, there was nothing in the lab, and we started almost from this flat ground, and we built the setup from there. So I'm trained to make setup. So that I'm trained to make instruments. So then that time I was actually trying to understand, can you actually translate the whole thing, whatever I am doing, can we translate it to the society? Because I belong to the, because I like to do some technology. And then fortunately, God gave me an opportunity to join the Technological Institute, where we are encouraged to develop technology. So we from 2018 we started translating it to the society. The very first equipment which we made was the whole slide imaging. It is nothing but is just the microscope. And if I say just the microscope, but it does a lot of things. It has auto-focusing. It has 4 objectives in there, and you just push in the slide, and it will do all the job. You don't have to really focus it. And then, so whatever slide you put in, so the whole scan it will actually put on the cloud, and then doctors can sit anywhere. They can actually look at the data from anywhere in the world. And this is dust-free device. And what actually made it dust-free, because we have actually logged it inside the optical tube where the dust cannot enter in at all. So in the next here, I will show you the movie where actually no, it's not. It should run, right? Play this one. No. So here it should come actually. Yes. It is starting. No, it's fine. It is fine. So here you see that this is. So this is the slide which we have inserted, and then you can move up and down there, and it can autofocus. And then along with that, what we can annotate the device, the area, the infected area, the cancer sites, and all. So these are basically designed for the biopsy sites, and you can actually annotate it. And we are actually trying to implement the AI as well, so that doctors just have to look at the slide. They can zoom in, they can zoom out, and whatever, they can keep revisiting it. So we don't have to store the slide forever. So you scan the slide, and and then after that, it can be stored forever. This data can be stored in the computer. So now the other device which I was actually talking about, for which we got grants for. So the idea came during the COVID time, where we wanted to really be wanted to have a minimal contact with the patient. Basically, the health workers should know we were not allowing them to go towards the patient, which were the infected patient. So how can we actually do the IV? And that is the idea where actually it came from. So in addition to that, when we were actually pitching for that, so this is when we looked into the data. So this is the kind of when a health worker gives a IV, the failure rate is something about 27%. And it increases in cancerous and the geriatric patient, pediatric patients, it can go up to 47%. And this increases when the first time if the failure happens, the nurses get stressed out, and then it with the human error, it can increase even further higher. So if the error happens at the first time, the second time making the mistake is more higher. So this is how actually it happens. So yeah, so the idea of this one is nothing but is basically we change the light source here. Light source is the near infrared, because just looking at this, I'm not able to see my veins, right? So, but we should be able to see the veins. We should be able to find the depth of it. And with our two eyes, so I mean, if I would have the only just one eye, I won't be able to perceive the depth. So because we have the two eyes, so that's why we are able to perceive the depth. And that is the principle which we want to implement here. So we want to use the near infrared light along with the stereo imaging. And then the data from here can be fed to the robotic arm. So this you have the two camera, what you see here in the middle, there is a infrared light, and this is me sitting in the COVID time, we were imaging that. So this is the vein which we saw. I mean, then and this is the overall schematic of the setup. So when we get the image, so we need to the image which we get. This is the original image which we got. So we had to do a lot of processing, a lot of Fourier transform. There are a lot of mathematical tools which exist. So this was just for the one image which we were able to pre-process the data, and we can actually process the image. And after that, the biggest challenge was to really how to find the depth out. So then there was a key point matching algorithm. So where we have the stereo two images, and we try to match the points, and then with that we can actually get the depth as well. I hope so it is there in the movie. So in the very first, this is how the workflow is. We have the stereo images, we extract the region of interest, we extract the vein structure, we generate the depth image. And then when we have this depth, then this 3D, we do the 3D reconstruction. This data will be fed to the robotic arm, and the robotic arm will be doing the job. And this was the first one. This is our second version. Prototype was already built. This is the second version, it is not yet tested because it needs human intervention. So that's why we did not. I mean, it is still under a lot of testing as of now. So I will show you a movie here. I hope it runs. Yeah. So this is how the equipment is. Over here, you can insert your arm. So you can insert the arm here. And then there is the syringe or the needle, whatever you can insert over there. So the imaging will be done by the cameras here. We get the stereo images there. Once the scans are obtained, we get we pre-process it. And once it is pre-processed, we get the depth of it. This is the 3D depth. And once we get the 3D depth, that depth information is given to the robotic arm. This robotic arm goes and actually does the IV. So this is how the setup looks like. Yeah. Yeah. So with this, I would so this whole work could not have been completed without my team. So this is quite a big team, but all of them don't work in just one area. So there are lots of experiments along. So I use TIFR facility where I use their laser system. So most of my experiments are set up there. The fundamental experiments are set up there. In IIT, we do most of the equipment development studies. And yeah, so these are the guys who are working in IIT. This is the top ones, they are working in TIFR. So these two are already graduated. They are actually, one is in Imperial College of London, one is in Max Born Institute. Yeah, and I would also like to thank the funding agencies, IITH, MOE, Spark, SERP, DSIR, and Shri PVF for that. And yeah, and thank you for all for listening me.
Thank you, Professor Vandana, for that truly interesting talk with this. Thank you for that really interesting talk, because it's one thing to talk and another thing to walk the talk. And you've actually demonstrated that you can do both. The session is open to questions from the audience. Yeah. Please wait till you get the mic. And
good evening, ma'am. As I'm a student of B Pharmacy and I'm in next. This is my final year running out. So next year I'm into the R&D research and development. As you showed the picture of IV infusion through the injection. If any error reading is there in the machine, how could he know the blood flow of the patient is correct or not?
So okay. So we are also trying to in the next generation, what we are trying to implement. There is a pressure sensor as well, and there is a flow meter as well, which we will be actually implementing there, which can actually measure the flow as well. And in addition to that, I mean, there can be an error. So there can be. I mean, before we do the IV, there will be a calibration process which will be going on. Okay, so if that is actually correct or not, we can actually test it on the phantom first.
Ma'am, my second question is, as the machine is as the construction on machine is all right, and how that injection will be injected to the veins and the blood flow will be correct, and how the caliber readings will be there. The caliber reading will be digital or digital.
Okay, so the amount of the solution. So I think that device already exists. The amount of amount of liquid goes into that or not. I mean, how much amount actually goes into that? That device already exists. So we are not making, we are not working on that part.
Okay, thank you.
Yeah.
Thank you for those very nice two different topics that you really talked about. I had some questions about the first part, because long ago for my PhD, I did atomic alignment collision dynamics, Steve Leone and others. So one thing is you talk about the dressed states.
Yes.
And so when you dress the states, your potential curves are also modulated.
So they're modified by 1 photon energy down there.
Right.
So
would it be really, I mean, but in what sense is it then a semi-classical treatment? Because you are necessarily having to look at a full quantum coupling calculation, aren't you?
See, semi-classical in the sense the kind of study, the kind of modeling we develop. So it definitely requires quantum mechanical calculation, which we are not expert at. We definitely need help.
Of course, these are also very difficult to model. Yeah, I understand. Right. The other thing is, so a small aspect. So here you're looking at the velocity vector correlations, right? I mean, so.
We are okay. So what can you elaborate?
No. So these are so you are correlating the initial polarization vector with the final velocity maps.
Yeah.
Right. And somehow then creating this narrative.
Yes, exactly.
There's also another way of looking at the polarization fluorescence from the excited states and correlating the from there they're getting the alignment and orientation parameters. Is that not? I mean, I suppose your spectrometer allows you this.
Only ions, yeah.
Ions.
So this we cannot do in this.
Right. Okay. Yeah. Thank you.
To see a presentation. So, also take daily presentation COVID time in ICU.
Yeah.
So,
How sorry?
Daily injections, ma'am.
You?
Yeah.
Oh. Okay.
ICU.
Are you?
So at the time, when we are given injection,
Hmm.
we have to put it in lay down
Yes.
properly.
Yes.
Then
Yes.
slowly we inject.
Yeah.
Then checking that is there any blood clot.
Yeah. Yeah.
So how do we test it?
So, so that is still, so these questions actually we are also asking ourselves, because since last 2 years, we are developing that. And there are many things which we need to really work on. So first thing is when we interviewed nurses and the doctors, I actually asked them that how do you feel when it goes inside? So everybody, the common answer was the pressure they feel. I mean, when they insert it, the pressure, when they try to insert, the pressure is different. When it is already inserted, that pressure is entirely different. And that is where we need to take the advantage of the technology, where we can actually put a sensor, the pressure sensor, which can actually tell us that this is, when it has already gone into the right place, the pressure is different. And then when it is going inside, pressure is different.
Yes, actually, they're injecting a high dosage antibiotic.
Yes.
When you start injection, it starts burning at the edge.
Agreed.
Then they're slowly injecting. They're seeing that, okay, are you pain here, any pain here, or any pain here?
Mm-hmm.
Like they're asking each and every moment that we are comfortable there.
Mm-hmm.
So after whatever observation, if something goes wrong, they'll give an explanation on this side.
Oh, okay.
So I feel the same thing. Their injection here after 1 year, it's a burn like anything to me.
Okay.
So they started giving antibiotic from here. So they take at least half an hour to get settled down.
Okay. Okay.
So in that case,
Okay.
and the investigation will keep like this.
No, you can actually, it has,
Like
you
this.
can, yeah. So we are trying to make it we will have the facility.
Yes.
If the patient is lying down, it can actually go inside. You can actually insert your full hand there.
Yeah, because this type of instrument is required. Because most of the people they're scared to give injection, especially in the ICU section.
Yes.
The specialized people, they're COVID patient. They need to go.
Yeah. So this is.
If this comes in the picture, so it is going to be rectified some problems.
So I don't want to really put as of now the hopes high. So the thing is, it will take another 2 to 3 years to come into the market, or maybe to give it to the trial, because it requires, to directly put into human, it is not justified. So it has to be tested multiple times, 1,000 times, 5,000 times, or lakhs times. If we are sure, then only it can be.
Ma'am, 1 minute. Please wait for the mic.
It is 100% safe side, or any effects are there in future?
As of now, we cannot say anything. Okay. As of now, we whatever results we have are on phantom. On phantom, it is doing correct. So we cannot say anything.
Thank you.
Very, very nice talk, Vandana, and really fantastic to see how things you have built up. I have a couple of questions. Maybe you said it and maybe something it's very obvious, but I may be asking something very obvious. So there are also these medicines which are slow release, like for cancer, they sometimes give you that they put an injection and then you know that it is there. So your thing will be also very useful for that.
As well.
Are you already working on that?
So that this device will be useful for that as well.
Okay. And does it therefore, because some of those are actually given at closer to the tumor at different places?
So it is only for veins, because we are able to image only veins. If as long as it is vein, it is fine, because we are working in the NIR region. So because we have this deoxygenated blood in the veins, so all the NIR gets absorbed there. So we are able to image it. As long as we are able to image the vein, we can do that.
But the veins just need not be on the hand; they can be in the different
so
parts of
it is
the body.
difficult. Near the heart and all, it is difficult.
Okay. Yeah. Okay. So this what they call central vein, where they sometimes
so it is deeper. It is deeper inside.
That is
below the ribs, right?
Yeah.
It is not possible.
Yeah.
Because the NIR can penetrate up to 5 millimeters.
Okay.
Yeah.
Okay. Yeah.
No. Yeah. Okay. So they do that.
Yeah.
Okay.
And then
I think there ultrasound guided injections help.
No, I was asking because for some of the tumors, cancer treatment, they put it in this because they wanted to mix in the blood quickly. They put
So
it in the veins closer to the heart, what they call the central artery.
Okay.
Even some medicines, when they are like fighting sepsis or something, they put it there to give the IV. So I was asking them. So and that is this main vein close to the this side. The second question I have is anyway, so as you said, it's more useful for where you can see the things closer to the surface. The second question I have is that having shown that this technique is now, of course, is very useful, and you have demonstrated that it is working, and of course, I hope it will get made into the product very soon. But what are the other things which you are looking at, or the next thing which you think can be thought of in this?
Okay, so we are also making very recently we started this glucometer thing. So we are still at the starting stage. So where now the idea actually came from one of my husband's friend. So his daughter actually has been having diabetes since very childhood, and she is being pierced all the time, and it's very painful for the father to see that, right? So the idea again started during the COVID time itself, but we could not pursue it because we did not have any resource. And resources in the sense we did not have human resources that time, neither we had any equipment lying in the lab. So but the idea was there. So because we are scientists, we know that this physics will work. So we very recently as one student we have actually put up, and we want him to work on that. So the idea is very simple. So the thing is, we have glucose, and most of human glucose actually is either L or S. It is not both. We have either L or S. I forgot that time. I remember that. So, it has the Faraday rotation. So the more the glucose level is, the more will be the rotation. Okay, and then it is directly proportional to that. So you just have to push the light in, and then you see that how much rotation it is, and then calibrate that rotation to the glucose level. And then you don't have to prick all the time. You will have the thing on the screen, like the oximeter you can make.
Okay, so that's of course very good. So now that you have told me this, I have one more question. So are you really thinking along in the directions of being an entrepreneur? Because you seem to have a lot of plans.
No, I'm not an entrepreneur, because for that actually you need really a big push. I cannot make people work for me. That is not a quality of entrepreneur. So I can work for myself, but I cannot make people work for me. So the team which works with me, they are actually they are self-guided people, and it is not like that I am guiding them. So it's God's grace that they are there with me, and they are self-guided, and they are working on their own.
I have a question. This is about that whole slide scanner that you had shown. We have worked on desiccation drying of droplets, including we tried with blood, but mostly on milk colloids. So what we found is using machine learning to actually recognize the patterns, because each drop is going to be unique, has really helped us. We intend on using some machine learning as the next layer to
this one.
Yes.
Yes. So there is a team. So I'm not expert at machine learning and AI. So there is a team who is actually working in this direction. So this is the version 1, version 2, which you saw here. So we after that we will be actually trying to develop it further, to use it for the research. I mean, this is as of now is only for the medical purpose, but this can actually be used for the research laboratories, and can be this whole thing will be integrated along with the AI.
I think even for diagnostics, I think the AI will be able to come through.
Yeah. So there are people who are working in this.
That's wonderful. Any other questions? Any more questions or comments from the audience? Okay. From the YouTube, we don't have questions, but we have some complimentary comments about the talk being good, and also that congratulations to ICWIP 2023 for a start to the conference. So on that note, let's all thank Professor Vandana Sharma for an excellent talk. And with this, we end the online stream for the public lecture. Thank you, Professor.
Take this.
Yeah.